Okay, so we left off talking about the actual turbocharger itself, not the whole system, but the actual turbo. So I said it's pressure oil fed plain bearing in the center of the turbocharger. And we've talked a lot about the oil there is very important. So I'll say constant oil pressure is critical. Constant oil pressure. Oil pressure is critical. One of the things that that gets messed up on these, it's a mechanic-induced damage that actually causes a pretty significant problem, is there's a check valve in the oil line that goes to this because you're going to use a scavenge pump to pull the oil out. You don't want the oil going backwards. So there's a check valve in there that keeps the oil going the right way. And mechanics often get that check valve in there backwards. So it's really critical to make sure that the check valve is always going the right way, because if you block the oil, it just seizes up in a very short period of time. So oil is supplied by the engine-driven pump, is supplied by engine, or by the engine-driven pump. That's just the same oil pump that's supplying the engine. Nope, I didn't want to do a C. What I want to do. The pressure is reduced. So reduced to about 30 to 50 PSI. Reduced to about 30 to 50 PSI. So a little bit of a pressure reduction in there. And you're going to run about 1 to 2 quarts per minute flow through there. And then oil may be returned with a scavenge pump. Okay, we've got the Y gate, The Y, actually, since say Y gate, it's called the Y. The Y provides paths, or a path to either the turbo or exhaust. So it's got the Y there that's either going to the turbocharger or the exhaust, and it also contains the wastegate. Well, the wastegate's actually attached to it. So you have the Y is more or less just a path in the road. Then we have the wastegate, which is the throttle, so to speak, of the whole thing. So the wastegate, it is a valve located in the exhaust line, exhaust line. I don't know what happened to my writing during lunch. I swear to you, I only had some beefy noodles, no liquid lunch. All right, when open. So when the wastegate is open, let's write that right. Exhaust gases leave exhaust and bypass the turbo to overboard. Kind of an awkward sentence, but there it is. Oops, I don't want to write a C yet. I want to write this. That is, we'll say this, turbo off. So open is off. So open equals off. And remember I told you it's never really all the way off, because you can't stop it. If you stop it, uneven heating across it. So that would be bad. And the reason why I say that is because there was always be a little bit of exhaust leakage across the Y gate if you tried to stop it. And so you would maybe it wouldn't spin, but you just have a little bit of blast of hot air. That'd be bad. So the wastegate never really lets it stop. So it keeps it just enough so that it's always turning. So C. Let's see. Yep, when closed. When closed, exhaust gases flow, don't say past turbo, no, through turbo, through turbo. And so that is turbo on. Turbo on, so closed equals on. And of course, they're just like you would with a throttle valve. The throttle valve, you don't say open is on and closed is off. It's just all the way open on a throttle valve is wide open and all the way closed is idle. Well, it's kind of the same thing. I'm just trying to make it easy for you guys to understand. So these are my terms, turbo off, turbo on. It's not really on and it's not really off per se. It's always on. But I'm hoping that if I can do it this way, you can grasp it a lot easier and go one way would be off, all the way would be on, and anything in between is just a partial opening. It's kind of on. So it's a mid throttle, if you will.
I have a question on like, I'm not sure how much it relates to aviation turbos, but on like a turbo on like a car, when you hear the spooling somewhere go, is that the wastegate opening?
No.
And then
no. Okay. So the things you're going to hear on a car, one, you'll hear the turbo spinning up, a real high pitched whine. That's just the turbo spinning. The other thing you often hear, especially if you are rapid with the throttle, you may hear the pop-off valve opening up to release the pressure. You won't hear that in an aircraft just because there's too much noise. And really, that's the last thing. I think I told you guys that my son hooked me up with he was friends with Westgate Ferrari, and they let us take one of the California Turbo Ts for a ride. And it was shocking. You know, I used to, my car does have a floppy paddles. And so, you know, I can floor my car and, you know, hit the floppy paddle. I floored that Ferrari in manual, thinking I was going to hit the pop-off valve. And I saw it had LED lights on the steering wheel. They went from nothing to red line faster than I could even comprehend. I mean, I just saw it, just wham. It was like less than a second. It was half a second or even a quarter of a second. And I saw it and I wham, and I'm like, whoa. And so I, you know, backed off of it, and then I heard this pow. And I'm like, oh, gee, I thought I broke the whole thing. But it was, it hit the rev limiter. And then the turbo spooled up so fast that it overpressurized or pressurized, and I backed off. And so it blew the pressure relief valve open, which is what it was supposed to do. So,
yeah, my truck does that if you're on it and then you just let off.
Okay, yeah, so it's normal. But does your truck go from like in first gear from no RPM to like red line and it was hilarious. It was so fast. Like, whoa. Thought I broke the Ferrari and I was going to have to buy it. That would not have been a good day for me. Okay, so three. I'm going to write about three basic types of wastegates. Types of wastegates. All right, three types. One, we could have a fixed type. Fixed type. Really, it uses an adjustable screw. Uses an adjustable. I wrote screw. I'm gonna put bolt because it's a lot bigger than a screw. An adjustable bolt to block a certain amount of exhaust. Certain amount of exhaust. To the turbo. So it's just like doing a wastegate that's partially closed. So remember, closed is on. So it's just partially closed all the time. So it's turbo throttled all the time. So it's not wide open, but there it is. So in a nutshell, what they've done is the engineers figured out we need exactly this much exhaust to go this way towards turbo. We need this much to go out. And we're going to put a bolt in there to fine tune it. So they fine tune it at the factory and they send it out. And I would hope that I would never have to try and adjust one of these bolts because it's probably welded in place by the heat and would never move anyway. So, all right. Okay, there's the fixed type. Then there's the manually operated. And the manually operated is just a pilot controlled push-pull type thing, just like you would. It's exactly like the throttle, but instead of being tied to the throttle, it's being tied to the wastegate. So the pilot just controls how much they want. The guy I flew with, the one time I flew in one that had an automatic, wasn't his airplane, so he really had fun with it. Treated it like a rental. So we took the center line and he just put his feet on the brakes and he brought the airplane up to wide open throttle. And then he just started closing off that wastegate. Remember, closed means on. Closing off that wastegate, watching his manifold pressure till his manifold pressure hit the red line, the max that he was allowed, and just took his feet off the brakes and away we went. And then once we started going, he started adjusting it back a little bit and then, just had to maintain it. So it's pilot operated cable. So pilot, there's different types of the manually operated. So pilot operated just with a push-pull cable. There is also one that is interconnected with throttle. Interconnected to throttle. And what that is you just imagine the cable going to the throttle, but it's the exact same cable just tees off and goes to the wastegate. So the whole thing is interconnected. So you only have one control. And then you think as a pilot, it's the throttle. So the more you push on the throttle to open it up, the more it's going to adjust the wastegate to give you the pressure that you want. And as you pull back, it's going to change the wastegate. So it's tied together so that the wastegate is doing what it needs to do and the throttle is where it is. So the two are just lined up and coexist together. This is more of a point. So there's the two types. I probably should have put two types in that, but I'll just say this. So manually operated systems use a pressure relief valve. Pressure relief valve in the upper deck. The upper deck to keep pressure from exceeding set limits. Exceeding set limits. All right, so that's our manually operated. Quite simple. The controls are really basic, and you have one safety device in there, and that's your pressure relief valve, just to keep the whole thing from going too high.
On fixed type,
yep.
Number 1, it says uses an adjustable bolt to block a certain of exhaust.
Certain amount.
Okay, thank you.
Glad one person's paying attention. Well, you're way behind. MJ, did you get a new dog?
Kevin.
Oh,
Hey,
yeah.
Kevin.
Yeah.
If this cable breaks, then you have a nice day, right?
You're gonna have a bad day?
Yeah.
Yeah. Well, it depends on how it's spring loaded. Spring loaded to wide open, which would turn it off. And so you wouldn't overboost. You'd just be down to normally aspirated, really.
Yeah. And then if that's the case, then you have to replace the cable.
Yeah.
And that one goes inside, or?
Oh, this is an external cable. It's not a big deal.
Oh, okay.
Okay. I hope everybody's kind of caught up with me here, because this is where this is be camping out on this idea here. It can be oil controlled. And the manually operated system, it's just that, right? It's not much, it's one step above the fixed. You more or less just manually control where you want the wastegate, and you pay attention to where your manifold pressure gauge is, and you just keep it within the set limits. And it's a lot of workload on the pilot especially because remember, you're trying to keep track of manifold pressure, which is now adjusted by the throttle, which is also adjusted by the wastegate. Then you have your prop control, and we're going to talk about some of the problems with these turbochargers, but I'm just going to sort of enlighten you a little bit with them right now as we go into this stuff. We'll just look at this one. You have to imagine that, and one of the problems with these that we'll get into is that because you have two separate systems, and so you're trying to control this valve here to control how much pressure is here, which controls how fast the engine is going. At the same time, you're controlling this, which controls the amount of pressure here, which ultimately controls the amount of pressure here, which you were trying to control with this. So if I set this at a certain point and I say, okay, my pressure between here and here is fine, and I open it up a little bit, well, then I'm going to let a little bit more air in. If I let a little bit more air in, I'm going to get a little more air out. A little more air out means I'm going to get a little more past here, which is going to then speed this up. And now I'm going to get more air than I wanted because I opened this up. Now it's going to shoot past. Now I got to bring it back. So it's this hunting back and forth. It gets really complicated with turbochargers. So you have that problem. Then alongside of that, of course, you just speed it up and you can live with the manifold pressure you got there. Or if it's too high, then you back this off. Or if you back that off, then you can lose a little bit here. If you lose a little bit here, you're going to lose it there. And then you got your speed starts falling off. And so you start chasing this around. So there's this whole problem with turbochargers hunting back and forth. And then there's also a thing called bootstrapping, where they tend to pick up, because they compress more air goes through here, because more air went through there, it goes through here, because it did that, it spin this faster, which makes that go faster. So the whole cycle just starts repeating. So they actually get quite complicated in how you want to control them. And so that's why with these aircraft, the whole idea of a manually operated creates a pretty heavy workload on the pilot. And like I said, we can even make that one step worse and go back and then, yeah, we'll go back. We'll just add complexity to this. So that was bad enough that we have these two that we're trying to deal with, but heaven forbid you actually touch the prop control, which changes the pitch of the propeller, which now slows the engine down. And so now you have an engine that just changed RPM. Well, that's going to have an effect on things. And so you change the RPM, which changes, it goes slower. When it goes slower, well, that means that this has building up pressure, which is now not being used to the extent. So manifold pressure is going to go up, and that changes it again. So manually controlled, I don't know, it just seems like it would be extremely hard. So what we have gone to, and most all of the systems have, is an oil controlled system throughout the whole thing that works with the wastegate. There we go, with the wastegate. So the way the wastegate works, if we kind of dissect and look at this thing, we can see that we have a spring here that is holding it back, which in this case is holding it open. So holding it open, I get, and you can see it here, it's already open on this one. So I get in my aircraft and I start it up. And unless something happens, you have to remember, this is in the open position, which is pretty much turbo off. This is the dump valve, if you will. So it's dumping, the exhaust is going to go through here and overboard. So that's great. But what happens, oil pressure, when it's allowed to build up, is going to come into here, oil outlet. So we'll go inlet there, we'll do it right. Oil is going to come into here and it is going to fill up, and this is a piston, and it's going to push on the piston. the piston is going to move this way, which is going to take this and start closing it. So throughout the system, and I'm going to show you how this works, is you're going to be, oil is really more or less sent to the controller once you start the aircraft, and this will slowly start closing once you start the aircraft and get engine oil pressure. And so it's normally open, but as soon as you start it, it wants to go close because oil pressure builds up. And then we're going to look at the controllers, and the controllers are going to work in conjunction with oil inlet and oil outlet to control the piston. And so I'm going to show you how that's going to work, but that's all it is. You just engine oil pressure, drain it off, this closed, cap this, it doesn't. So oil comes in, and if I have a cap right here, as soon as you built up oil pressure, it's going to make this thing open, close, turn on the turbo, and it will always be on. And then if I unscrew the cap, then oil comes in and drains out of here, and this would close. So kind of works in that.
Okay.
Yeah.
Does the pilot control these, or?
Nope. These are all automatic. So once they get into oil controlled, 100% automatic.
So when you slow down and you land, before you turn it off, you said you want to get the turbo to spin slower, right?
Yeah.
How does it work that way?
Well, simply because you pull back on the throttle, upper deck's going to build up. And because upper deck builds up, all the pressure controllers are saying, wait a minute, we're already at 30 inches. You know, it's at 29 anyway, because you're ambient. If it's set for 30, it's going to take 1 inch of pressure and go, we're done. We don't need any more. Just go ahead and open up that wastegate. So it takes almost nothing at an idle. So I'll go through some of the drawings here a little bit. We'll talk about them. There's going to be a lot of different systems. Don't let that freak you out. They all work almost the same. So, and this is all we've looked at already, right? So we have ambient air coming in. You have the compressor in the center. It goes, okay, this is the manual one. So I like how they depicted that. It looks just like a faucet on here or something. Nothing more than a pressure relief valve. And in my notes, I said the pressure relief valve was set at the upper deck. I believe that some of them, there's no reason why you can't put the pressure relief valve, I suppose, on the throttle side, on the manifold. I believe that they always put it on the pressure relief side, because if you put the throttle valve here and close this off, let me see, because this works so great. There we go, works better with this pen. So if I were to put my throttle valve here and close that off, well, then how am I controlling this? So I could get way too much upper deck pressure. So I think that's why they always put the throttle valve here and not over here. That way you're actually controlling, the upper deck pressure and what the compressor is doing, so you don't have too much pressure here. And then the throttle then controls manifold. So it works that way. So air goes through here, it gets to the Y. So here's my Y. And remember, Y is just a passage one way or the other. And if the manual wastegate controlled by the pilot is in the closed position, then closed means on, all of the exhaust gases are going to go through the turbine and out. If the wastegate is all the way open, then some will go this way to keep it turning, but most of it's going to want to go this way, and very little compression happens. Then I said there was the mechanical interconnect, which is just the throttle valve, or the throttle in the cockpit, if you will, just connects at one point. So when I move that, I move both of them simultaneously. So as I open the throttle and demand more turbo pressure or turbo pressure output, then it's going to want to close this off, the wastegate, and the exhaust gases, instead of flowing through the Y this way, they flow through the Y this way, increase turbo speed, and off we go. And I like this drawing because it actually put the pressure relief valve right over here where it's clearly and obviously in the before the throttle. So this is, remember, this is upper deck. So if when upper deck exceeds what it should be, the pressure relief valve is just going to open up and bleed off all the extra, keeping it at a safe limit. So you can't necessarily overboost it. Now this one, of course, you could overboost the engine, because remember your gauge right here is going to be manifold pressure gauge. You could exceed it if you're not careful, especially if you're jazzing the throttle really quick and you didn't have this connect, or the interconnect working correct rate, or the pressure relief valve was not adjusted correctly, but they don't usually go out. I want to get into this one now. Trying to decide. Well, why not? I showed it to you. Okay, so I'm gonna show you how this works, just like we've done before. You may kind of go back and go, what the heck just happened? But we're gonna cover it again. Now I want you to look down here. This is the Lycoming density / differential control system. There's gonna be a lot of different systems. So let me see, Lycoming's got the differential density, it's got differential pressure, we got all kinds of different ones. Lycoming, even Continental to a point, well, especially Lycoming, it's almost like they go to the shelf and they've got all these different controllers, and for some reason they decide, hey, on this one we're going to use 2, and on this one we're going to use 3, and on this one we're going to use this one that acts like those 2, but it's 2 in 1. And that's where it all gets confusing. But the way they all operate is nearly the same. And if you can understand the basics, you can always go back to this and just look at it. Go, okay, understand the basics. Basics will get you through it, and you just reverse engineer from that point. And they're not hard, just once you get the basics. So, all right, that's why I like this one, because it's got 2 controllers and it's reasonably basic. So first of all, let's identify 2 controllers. 1, we've got a density controller, and 2, we got a differential pressure controller. All right, here's our turbo, air inlet. Here's the turbine side, here the hot side, here's the cold side, and here's our wastegate, which we know is spring-loaded to the open position. All right, so let's look at our controllers here. So, and we'll go back and write stuff about this. We're just gonna look at it for right now. So we know that air comes in here and it is compressed in the compressor. It goes up through, and we call the blue
Upper deck.
upper deck. Probably good. I don't have you guys, your picture open. Wasn't even sure if anybody was with me. There we go. Now I can see you guys. Okay, so we've got our upper deck pressure. Now they're going to call it compressor discharge pressure, but we're going to call it upper deck. We have our throttle valve, and from the throttle valve on the other side, we have the manifold pressure, right? Obviously cylinder, exhaust, Y, because that's what Van Halen saw. Y is a crooked letter. I forgot. I want to say it every time. The Y, we have the wastegate and the turbo. All right, so now we're using these controllers. Let's start over here. So we know that this is normally open, but any sort of oil pressure is going to close it. Oil pressure is going to act on a piston. The piston is going to close it. So let's take a look here. So we have engine oil pressure inlet starts right here. So it comes right off of the engine and is fed to this. No controller, no nothing. Straight shot, boom, fresh oil right there. It fills up this cavity. It runs through here, around, out, over. It's going to go into density controller. Through the density controller, it doesn't show it real well, but it's going to go through and right here. This is oil return to crankcase this side. So this should be yellow too. All right, just like it is over here. So over here, they've got it colored properly. I could color it if you'd like, because, you know. And while I'm drawing this in, I guess it is worth mentioning that I did complete 4 books during my spring break, which if you think about it, that's a lot of coloring. So, all right, so that's all yellow going through and yellow to crank. That was a joke. See, I colored on my thing. All right, good.
Nice joke.
Nice, all right.
I thought you read 4 books.
No, I just said I finished 4 books.
I read 2 books.
Okay, so oil comes around, goes through, it flows through here, drain to crankcase, drain to crankcase. Okay, that's an important point right there. As long as this drain is open, and as long as this drain is open, no oil gets to build up in here. It just comes through here and goes to drain. It just takes a long way through drain, and it goes through a bunch of controllers. But if I have oil coming through here, and right back to the engine, how much pressure gets built up here?
None.
Exactly. No pressure gets built up here. And if no pressure gets built up here, then this doesn't do anything and it stays in the open position. And if it stays in the open position, that is turbo
off.
Off. Okay. So we know that. Now let's look at what these two controllers do. And a lot of times they name them in a way that helps us out. So we can start here, the density controller. All right, the density controller actually senses the density of the air in the upper deck. It's density. So I kind of want to say its job is to say, hey, I want 30 inches of density air. And that's what I want. And you're going to give it to me. And so we have two people though, one guy over here and one guy over here. So this guy's, his job is, I want density. All right. Just all he keeps saying, I want density. And well, you know, you can't have too much density. Kevin told us, you know, you're going to overheat, you're going to burn the engine. I don't care. I want density. So that's what this guy, he just wants density. And until he gets his right density, until this guy over here, wow, sorry about that. Until this guy gets density, he is not going to open up. He's going to shut down, close off, and keep this. Sorry, I want my pen. I want a black pen too. We'll do black. So until this gets its density, boom, that is closed. So no oil gets drained off. So as far as this one is concerned, he says no oil gets drained. If no oil gets drained, then the oil is going to build up pressure back here because the engine keeps feeding it in and it's got nowhere to go. And this is going to pressurize and it's going to close, right? So if we only had one controller and we only had a density controller, that's all this thing would do. It would just keep it at 30 inches, the proper density of like 30 inches and never care about anything else. All right, but that could be bad. All right, it could be bad for a couple of reasons we'll talk about later. But so we got to put somebody with some brains in the operation here. I guess this is kind of like a marriage. This is me over here. I want my density, but here's my wife over here who is, you know, infinitely smarter and says, well, don't be an idiot. You know, you got to think this through. You're going to get to a point where you're over, the turbo is working too hard and it's going to create too much heat and all these other problems. So we don't want that. Let's be smart about this. So let's pre-plan this out. When we get to a certain level, certain altitude, you got to start backing off a little bit. Well, we call that the critical altitude. And so the differential pressure controller kind of figures out that by sensing the difference between what is here and what is here. So it's looking at the pressure across those two. It does it in a roundabout way. It's picking it up right there, and this line goes right over here. So that one is the differential pressure controller. Now, one of the other problems, and I talked about it a little bit, could you imagine if you had a huge amount of pressure build up on the blue and not very much over here on the green? There's very, very little. The valve is pretty closed. If you even looked at the throttle too long in the cockpit and it moved a tiny little bit, this dam here is holding back this huge flood of air. Just the tiniest little movement is going to, the air is going to be flooding in. So you want to increase your throttle by 100 RPM, you're not going to do it. Fat chance. Because even the slightest of slight movements, you'd have to have one of those veneer ones and you just barely touch it. And just it squeaks open a tiny bit and whoosh, all right, there it goes. The throttle starts taking off. The engine starts going too fast. Like, oh, I barely touched it. Yeah, I know. You barely touched it. Now the throttle just went crazy. All this air floods in through here. It floods through here, running across the turbo wheel. It spins up more and you're like, well, I didn't want that. So the differential pressure controller is the brains of this operation over here. And it says, wait a minute, let's think this through here. We shouldn't have really more of a spread than a couple of PSI across here. And as long as, otherwise the turbo is just working too hard to build up all this density we didn't need anyway. So let's just measure across here and let's just give it a couple of PSI. I'm just going to say 2 for right now because I remember what it was off the top of my head, but I think it's about 2 to 4. So we're just going to hold this here about 2 to 4 PSI. Anything more than that's ridiculous. We don't need it, and it causes turbo sensitivity. So as soon as this gets to more than 2 PSI, it just opens up. It dumps all the oil out. This guy over here is saying, I want more pressure, but this one says, I don't care. I'm going to open up. And all that, I'm just going to dump out all the oil. So it doesn't matter what you want because I just gave it a way through. And so all the oil from here starts draining off. Well, it doesn't necessarily drain off. It drains off to a point where this opens or closes to where it should be to maintain this proper differential. And then this closes back up again. And, you know, open up a little bit and drain a little oil, close a little bit, hold it in, you know, just kind of, it's always moving a little bit, doing what it needs to do to keep this thing at its point, keeping it what it wants to do.
Is that a diaphragm in there?
Yes, it is. A diaphragm with a spring. It's all these things are diaphragms and springs and aneroids. This one I think has got an aneroid. This one here's got a spring. So this one's aneroid because it's sensing air. So it's got to have an aneroid in it. This one is diaphragm because, and a spring because it's a differential between two things. I'll write this stuff down for you. So I can take this system and honestly, all I can do with any other system is just add different controllers, which are nothing more than different personalities trying to do something different. But for the most part, this is it. This is everything. You just add different controllers that are sensing something else or doing it in a different way. But every single controller from here on out, every single system that uses oil does exactly this. Supplies engine oil pressure. There it is, laser pointer. Supplies engine oil pressure to a wastegate. If you block off the wastegate outlet, the wastegate closes. When it closes, it turbo ons, or more turbo. You open up a leak, drain it off. This thing goes the other way, opens up, less turbo. That's all it is. And so then from there on out, so every single wastegate is all the same. Lycoming, Continental, whatever. They all work the same way. They all need the same maintenance. They all taste the same. And then from there, you just change out controllers. Sometimes Lycoming will use these two. Sometimes they're going to use something a little bit different. Sometimes they use three. Sometimes they're going to call them crazy names and they don't know what the heck they're supposed to be doing. But that's all there is. So we'll talk about those.
So how does the differential pressure control deal with the critical altitude?
Doesn't know anything about it.
Okay, but you said it kind of deals with that?
No, let me go back to that. That was a really good question. I didn't finish this. All right, so if I want to follow through on that thought process, because I like that question. Okay, so this over here, I just want density. Okay, that's all it keeps saying. Well, that's its job. The differential, it knows nothing about density, nor does it even care. It's the furthest from the mind there. So we'll do this one. So at some point, remember, it's always trying to measure the difference between these two. And right now, with this closed, it's saying, look, we've got more than enough air here in the upper deck. You've got a vacuum practically over here, where you do have a vacuum, actually, not practically. You do. You got a vacuum over here. So if you got a vacuum over here, well, how much pressure we need here? We don't need any pressure hardly. So knock it off. You know, what would it be in PSI? I should have a chart handy. Does anybody know offhand? What is, we should look that up. What is in absolute pressure wise, 10 inches, see 30 is 14. So let's just dump it in half and say, well, it'd be a third actually, a third, 14 divided by 3. So, well, 5. So let's say we got 5 PSI. Remember, it's absolute. It's actually a vacuum compared to the outside atmosphere. So if that's 5, this doesn't work out quite well because this wouldn't be a vacuum for any reason whatsoever. But you only need 7 PSI here. And, but hopefully you can see what I'm trying to say. If you have 5 here, only need 7 there. All right. But then I decide, well, I'm going to open up the throttle. And because I do that, I got to erase this. So I'm going to open up the throttle. And so because we open up the throttle, and we open it up quite a bit, let's say, and at some point we've got it most of the way open, and we've got 26 inches over here. Well, we'll talk in terms of inches. This over here says, yeah, not 2 PSI, 2 inches. This one says, well, I don't really need to be anything over 28 inches. So it gets to 28, it's going to sense the difference between these two and say, okay, well, anything over 28, we don't need it. We don't even need 30. Just 28 is fine. All right, then we get to a point where we're wide open throttle, right? We're wide open. And over here, I want to see 30. We'll say it's normalized. I want to see 30 here, no more than 30 because it's normalized. Well, then this is going to say turbo, you better be putting out maybe no more than 32 over on this side. And all along the density controller is going, give me 30. All right, we go way up in altitude, okay? Going way up in altitude, and the manifold pressure starts dropping off. Well, now it's at 28. All right, and let's see. So it should be up at 30. And the reasons why it's not there, this says, well, wait a minute, hold on. We're not putting out enough. We got to get to 30. Give me more, go to 30. So it does that, but when it gets to 30, it starts working. And now this over here, the differential isn't working because maybe it's 28, 29. It's going, well, shoot, we need more. But this thing over here is saying, I can't give you any more. I'm doing the best I can. We've reached the density. We've reached the heat limits. We've reached all the other stuff. So it's finally starting to work. And we start coming down in manifold, but over here, differential's going, well, I don't really see that. And so we could even get to a point where we could have a big split. We could say, because the throttle's partially closed, we've got 28 over here and we've got 30 over here. I will drop this one down to 27. And now we've got a split of 3 and the differential is saying, no, we need more. Or am I doing that right? I might have just went backwards on that, sorry. But before I screw it all up, I hope you get the idea that they work very independently. And so differential's always looking to get the differential. And at some point, the differential pressure, it's going to be not satisfied and it's going to say, hey, we need more turbo. But yet the density is going to say, well, wait a minute. Now we need to think this through. No, we've got the density maxed out on this because of one factor or another. And no, we're not going to do that. So that one takes over.
Hey, Kevin.
Yeah.
So the density, if you go back to the picture.
You want me to go back to the picture?
Yeah.
Okay.
Yeah, the differential pressure control.
Uh-huh.
It is tied to the density controller, right? Or completely independent?
Completely and totally independent. The only thing that they share in common, well, they share 2 things in common. One, they both sense upper deck. And this one's over here on the right, and this one's over here on the left. So this is, it's the whole units right here. So they both share that they sense upper deck, and they both share that they both have a say in what happens to the oil, but independently. The density controller could say, I want to, and in fact, even in this case right here, the way they drew it, they've got it blocked off. They're saying density controller is more than satisfied. It is getting all the air that it needs. And the pressure it's saying, stop, you need to stop this right now. We're maxed out. And the differential pressure controller is over here is saying, wait a minute, drain off. We've got too much. You've got too much. You got to start draining. Actually, I'd say, I take that back. This is saying we don't have enough. Density controller is saying, I need more turbo. So it's shut down. It's blocked it. It's telling the wastegate that you need to start closing. Give me more turbo. So this one right here is saying, need more turbo.
Oh, okay. I got it. I got it now. I got it backwards before. I thought the oil needed to go through.
Nah, it's probably because
in order to open.
Okay. So I'm glad you asked. I'm sure there was at least 4 other people like, oh man, thank God he asked that question. And so right now this differential, especially because this is closed, and that's really the reason why, because you're going to get a huge pressure differential across these 2 if it wasn't for this one right here. This one is saying, whoa, we've got a really big pressure differential and we don't want that. That is going to cause so much sensitivity that it isn't going to work. So drain, turbo off. And so it's draining out. It's closing this thing off right now. Sorry, it's opening this off, opening it to let more go through. Okay, Gaddy's got to keep me honest because boy, it starts getting weird when I say open, opens, close, open. All right, let's see. So let's talk about this one. So this one specifically, this is the Lycoming differential slash density system. All right, this particular one, not that this matters, and you guys know I'd never test you on this. It's a TIO 540 540 alpha to alpha, used on the Piper Navajo. Used on Piper Navajo. Piper Navajo. It is sea level boosted. Boosted by 10 inches. So would I call that a normal, turbo normalized or boosted?
Boosted.
Boosted.
Boosted's correct. Oops. I think I skipped a whole bunch of stuff here. I'm sorry. Well, you know what? That's a good place to stop then. So I'm gonna actually end up erasing this right here and putting in some other stuff right up here because I missed some notes. But we'll do that tomorrow. And that would be a good place to end it tonight. So 7:50. Before I do let you guys go, I'll stop this real quick here. I just wanted to stop recording.